Students, good afternoon. Good afternoon to all of you. So, students, can you able to hear my voice? Good afternoon, Vaishnavi. Good afternoon. Yes. Yes, Rituja, good afternoon. So, all of you can able to hear my voice, right? Sakshi is saying yes. So, I think we can start the today's session. My voice is clear now? Yes. Okay, thank you, Sanika. Fine. So, let's move on to the session. So what we have discussed yesterday regarding the order of the reaction. Okay, mainly we have discussed about the order of the reaction and something related with instantaneous state and all. So now I'm going to ask you a question, very simple question only. Okay, I'm going to ask you a definition and you guys are going to give me the answer. What is an order? What is an order of the reaction? Can anyone give me the definition in the chat box? What is the order of the reaction? Or what is, can you define the order of the reaction? Can anyone give the definition? What is an order of the reaction, my dear students? Sakshi, Rutuja, Sanika, two Sanikas are there. Sandana, Vaishnavi, Jyoti, Pratyusha, Mahek. So yesterday you guys were there in the class now. So what is the definition for order of the reaction? Sum of the power of the concentration of the reactant in the rate law expression. Okay, don't forget that in the rate law expression. Very good, Vaishnavi. Kanika, good. So, this is what we have discussed yesterday. And order can be fractional and it can be an integer and rarely it may have the negative values. Okay, so these are the 2 points which you have to keep in mind. And also we have discussed about the elementary and complex reactions. So, which is the rate determining step in the complex reaction? Slowest step or fastest step? Which is the rate determining step? Slowest step. Very good. So, don't forget these points. These are very important theory points. Okay. So, you should not have some confusion or should not have some doubts here. Yeah, yes, Vaishnavi. It is a slowest step. So, today, as I have discussed yesterday, so we were about to discuss about the order and molecularity yesterday, but because of time, we could not go with the molecularity. So we have completed only the order of the reaction. So today we are going to look into the molecularity of a reaction. Okay. Now, what is molecularity of a reaction? The number of reacting species. The species can be the molecules, the species can be the atoms, or the species can be the ions. Okay. So the number of molecules, the number of reacting atoms, the number of reacting ions taking part in an elementary reaction which collide simultaneously to bring about the chemical reaction. Okay, it's called as molecularity of a reaction. So, if you go for an elementary reaction, so elementary reaction takes place in only single step, only one step. So, the number of reactant molecules taking part in that reaction is called as the molecularity of the reaction. If we are going for complex reactions, as we have discussed yesterday, we may have more than one step in those reactions. So what we have to do, we have to look for the elementary reaction. Okay, and the number of reacting species taking part in that elementary reaction in all those steps. So that is called as the molecularity of a reaction for complex reaction. Okay, so you'll discuss some examples so that you can understand it better. So the number of reacting species taking part in an elementary reaction which collide simultaneously at the same time to bring about the chemical reaction is called as molecularity. Okay, so take down the definition. Now let's see some examples. So I am going to take N2 plus 3H2 giving 2NH3 reaction. Okay, now we are going to apply the law of mass action. So we have studied law of mass action in the what to say, in the Friday's class, I think. In Friday's class, I think, yeah. So now applying the law of mass action, the rate is directly proportional to the concentration of the reactant. So one of the reactant is nitrogen and the number of moles is 1. And with respect to hydrogen, it is 3. So this is the rate. Rate depends on the concentration of nitrogen and hydrogen. Okay. Now here we have only one molecule of nitrogen, so it is 1. And for hydrogen, we have 3 molecules, so the order is 3. So 1 plus 3 is equal to 4. Now this 4 is nothing but the molecularity for this reaction. The number of reacting species, okay, in a reaction. So 4 molecules of these reactants are reacting with each other. So the molecularity is equal to 4. Clear for all of you? Very easy now. So this is an elementary reaction which takes place in a single step. So there are 4 molecules involved in this. So the molecularity is equal to 4. Shall we go with one more example? Any doubt from the molecularity part? Okay. So now coming to one more reaction, the decomposition of hydrogen peroxide. So here we have only one reactant. Okay, here we have only one reactant. So obviously the rate of the reaction depends only on the concentration of that particular one reactant. Okay, so since we have only one reactant, it is called as unimolecular reaction. Okay, and coming to one more example, NH4NO2 giving N2 plus 2H2. Here also we have only one reactant which is called as ammonium nitrate. So it is also the unimolecular reaction. Okay, so the molecularity of the reaction in these two cases is equal to 1. Got it? Now here, in 2HI giving H2 plus I2, how many reactant molecules I have in this reaction? Can anyone try? Can anyone try the answer for this? How many reactant species are involved here? Very good. It is 2. So it is a bimolecular reaction, or the molecularity of the reaction is 2. Okay. And what about this reaction? How many reacting species we have here? We have one NO and one O3. Yeah, yes, Mahik. So the answer is, it is a bimolecular reaction. Molecularity is equal to 2. Very good, very good. Yes. Now let's move on to one more. 2NO plus O2 giving 2NO2. So what is the molecularity for this reaction? Yeah, it is 3. Very good. It is 3. It is a trimolecular reaction. Very good, students. It is a trimolecular reaction. So now you have got the point, right? The number of reacting species taking place in a elementary reaction is called as molecularity. Okay. Now moving on to some more information about this molecularity. So the molecularity can be 0. Can molecularity be 0? So what is your answer for this question? So this is the question actually. Okay. Can molecularity be 0? So what do you guys say? Can it be 0? Can we have a reaction with the 0 molecule? No. Okay, at least one molecule is required for a chemical reaction to get converted into the product, right? So molecularity cannot be 0. But order, if you think from yesterday's class, order was 0. So we had 0 order reactions, okay? But molecularity cannot be 0. Okay, and one more question I am going to ask. Can molecularity be -1, -2, etc.? Can molecularity be negative? Rarely order was found to be negative, no? What about molecularity? No, we cannot say that we have -1 molecule or -2 molecule, right? Yeah. So molecularity cannot be negative. So can it be fractional? Can it be fractional? Can molecularity be fractional? Yes. No. Answer is no. Okay. Molecularity cannot be fractional. Okay, Mahek? So it cannot be fractional. It cannot be fractional values. So molecularity, what to say it cannot be zero, it cannot be negative, it cannot be fractional. So it is a theoretically obtained value. So it cannot be determined experimentally. It can be determined only by the theory point of view. Okay. So it cannot have the experimental proof. So order is an experimental quantity, but molecularity is a theoretical quantity. Got it? So these are the informations we are learning, we are getting from the molecularity of a reaction. So now with the informations we have got from molecularity, let's solve some MCQs. Okay, so do any of you have any doubt from molecularity? So the definition is very important. Okay, the conceptual understanding of the definition is very, very important. And we have seen some examples. And it cannot be zero, it cannot be fractional, it cannot be negative. So these are the points you have to keep in mind. So let's move on to the first question. Which of the following can be the values of molecularity? Option A -1, option B 0, option C 1 by 2, option D none of these. Which of the following can be the values of molecularity? Yes, very good students. It is option D because it cannot be negative, 0 and fractional. 1 by 2 means it is 0.5, it cannot be fractional. Coming to the second question, what is the molecularity of this reaction? 1, 2, 3 and 4. The same example we have discussed in the class now. Yeah, it is option 1. It is option 1. What is the molecularity of trimolecular reactions? What is the molecularity of trimolecular reactions? Is it 1, 2, 3 or 4? It is 3. Very good. The option is C. So now we are going to discuss about the difference between order and molecularity, which is very important. Okay. So in the tabulation form, we are going to discuss the differentiation between this order and molecularity. Okay. So let me take a tabular column. So first we are going to discuss about order. The next column is for molecularity. So first of all, I'm going to give you the definition for both. Okay, so order is nothing but the sum of the power of the concentration term involved in a rate equation is known as order. Okay, and what is molecularity? The sum of the power of the concentration terms involved in the law of mass action. In the law of mass action is called as molecularity. So here law of mass action and here rate equation. So this is the only difference between both. Okay. So this is the definition. Next, coming to the second point, order is an experimentally determined value which is valid for elementary reaction as well as for complex reaction. We can write the order for elementary reaction and also we can give the order for complex reaction. So in case of complex reaction, so we will be taking the order in accordance with the slowest step. Okay. But molecularity, if you see, it is a theoretical value which is valid only for elementary reaction. So it is an experimental value and here is a theoretical value. It is valid for both and here it is valid only for elementary reaction. Okay. So this is the second point. Now moving on to the third point, order can be zero, fractional or integral, integer, and rarely it can be negative. So already we have discussed about this yesterday. And here molecularity can never be zero, fractional, and it always has a positive integral value. Okay. So clear? Clear up to this point? Shall I move on to the next point, students? All these differences are very important. And order of a reaction depends on experimental conditions, and molecularity is independent of the experimental conditions. Because order is an experimental quantity, molecularity is a theoretical quantity, so it is independent of experimental conditions. Okay. So the next point is, order gives an idea about the rate of a reaction, but molecularity does not give any idea about the rate of a reaction. Okay, clear? So for complex reactions, if you see, the order is given by the slowest step, and molecularity of the slowest step is taken as the order for the overall reaction. Okay. So for complex reactions, we may have two steps. Among those two, one is the slowest step. No, the number of molecules taking part in that slowest step may be two. So that too is taken as the order for overall reaction. Got it? So these are the very important points about order and molecularity. I hope this 5 points are very clear to all of you. So do you have any doubts? Shall we go with one question from the order and molecularity? Yeah. If the molecularity of a reaction is 2, then the reaction is said to be unimolecular, bimolecular, trimolecular, all of these. What is the answer? Yeah, it is bimolecular. Very good. The sum of the powers of the concentration terms in rate law expression is called as index, order, molecularity, none of these. What is the answer for this? In the rate law expression. Very good. It is called as the order of the reaction. Very good. Then, the reactions with molecularity greater than 3 are definitely dash. Reversible reactions, complex reactions, both A and B, none of these. Reactions with molecularity greater than 3. If more than 3 molecules involved in a reaction, then it is called as a very good. It is a complex reaction. Very good, students. Question number 4. Dash and dash are theoretical concepts. Order and molecularity, rate law and order, law of mass action and molecularity, none of these. Which two are the theoretical concepts? Option C. Sure. Okay, option C is the correct answer. Law of mass action and molecularity. They are the theoretical concepts. Very good. So with this, we can close the order and molecularity topic. So the next topic is the new topic to you guys. So I hope everything is clear so far. Shall we go with the next concept? So next we are going to discuss about the rate constant. Shall I move on to the rate constant? No doubt now till the molecularity topic. Okay. So let's move on to the rate constant and its characteristics. Okay. So can anyone tell me the notation we use for rate constant? So rate constant is denoted by which letter? Yeah, it is K. It is not Kc. It is not Kc, my dear. It is K. Okay. Rate constant is denoted by the small letter K. Very good. Rate constant. Rate constant is also called as specific reaction rate. Rate constant is also called as specific reaction rate. Okay. Suppose if I have A plus B giving C plus D reaction, the rate of this reaction is directly proportional to the concentration of the reactants raised to some their stoichiometric coefficient. And here I am going to take that stoichiometric coefficient as alpha and beta. Okay. So therefore, rate is equal to, if I remove that proportionality symbol, I will introduce a constant. That constant is called as K, which is nothing but the rate constant. So K is equal to the rate constant. And that rate constant is equal to rate divided by the concentration of A and B. So if you take this entire A and B to the other side, it will go to the denominator, no? So K is equal to rate by the concentration of the reactants. Got it? K is equal to rate divided by 1. If the concentration, if they are equal to 1, if you multiply those two and if it comes out to be 1, then K is equal to the rate. Okay. So definition for rate constant is, it is defined as the rate of a reaction at unit concentration of the reactants. What is rate constant? It is the rate of the reaction at unit concentration of the reactant. Unit means 1. Okay. If the concentration is equal to 1 for the reactant, then rate constant will be equal to rate. Okay. So this is the definition for rate constant. Now we'll move on to some cases. So first we will discuss about the units. Okay. So we will discuss about the units of rate constant. So first of all, I am going to discuss with you about the unit of the zero order reaction, unit of rate constant for zero order reaction. Got it? So here we are going to discuss about the units of rate constant for zero order. So to find out the unit, so take the rate equation. Rate is equal to K into A power 0. Because since it is a zero order reaction, order should be equal to 0, right? So it is equal to K into, it is equal to K, and the concentration is, and in place of rate, you can substitute mole per liter per second. Okay, rate is nothing but the concentration with respect to time, dx by dt, right? So dx means it is a concentration. The unit of concentration is mole per liter, and the unit of time is second. So mole per liter per second is taken as the unit for rate, and that is equal to K. Because anything to the power 0 will go to 1, no. So it is just equal to K, and the unit is coming out to be mole per liter per second for zero order reaction. Okay, mole per liter per second. Clear? Shall I go with the unit for rate constant for first order reaction? Shall we go with the unit of rate constant for first order reaction? Yes. So for first order reaction, what is the rate expression? Rate is equal to K into A power 1. So here the order of the reaction is 1. So what I have to do in place of rate, you have to substitute mole per liter per by second, which is equal to K, which is equal to concentration. Concentration is nothing but mole per liter. Concentration unit is mole per liter. Okay, so in place of concentration of A, substitute mole per liter. And if we cancel out these two mole per liter, then we will get K is equal to per second. So the unit of rate constant for first order reaction is per second or second inverse. Okay. So next coming to the unit of rate constant for second order reaction, the rate will be equal to K into A power 2. So it is mole per liter by second, which is equal to K into mole per liter square. And if you square everything, so K will come out to be 1 by mole per liter second. Okay, because 1 mole will get cancelled out each other. If I square this, what I will get? I will get mole square and liter power minus 2, right? So 1 mole will get cancelled out each other, and 1 liter's inverse will get cancelled out each other. Okay, and if it goes to the other side, we will get liter, mole inverse, second inverse. Okay, so the unit of rate constant for second order reaction is liter, mole inverse, second inverse. Okay, now how to find out the unit of rate constant for different order of reaction quickly without doing such kind of calculation? We can also get the unit of rate constant for different order reactions quickly. Okay. So I will give you one formula to find out the unit within a fraction of second. So before going to that formula, you are going to tell me the unit for third order reaction. Third order reaction means order will be 3. So can anyone get the value for unit of rate constant for third order reaction by substituting all the values like this? Just get the value fast. Get the value for the unit of rate constant fast. K will be equal to 1 by mole square per liter square second. So what is the value? So it is liter square, mole inverse power minus 2 and second power minus 1. So the unit of rate constant for third order reaction is L square, mole power minus 2 and second inverse. Okay. So like this, if I have to find out the rate constant for any nth order reaction, it can be fourth order reaction, I can calculate the unit for fifth order reaction, so it can be anything. Okay, so to find out the unit for rate constant for any nth order reaction, I am going to use one formula. Okay, you can go with the same method itself. So, and that formula is here. So, it is K is equal to mole by liter. Mole per liter 1 minus N second inverse. Where this N is the order of the reaction. Suppose if I want to find out the unit of rate constant for second order reaction, substitute N is equal to 2. If you substitute N is equal to 2, what you will get? 1 minus 2 is minus 1. So it will be mole inverse, liter, okay, and second inverse. So this is what we have got now for second order reaction. So use this formula and you will get the answer for any order reaction. What is the unit for rate constant for fourth order reaction? Can anyone give me the answer for this? For fourth order reaction? To find out the unit of rate constant for fourth order reaction, what we have to do? Substitute N is equal to 4. Substitute N is equal to 4 and let me know the answer in the chat box. Okay, mole power minus 3. Okay, so many of you are giving me different answers. So substitute N is equal to 4. So it will be 1 minus 4, we will get minus 3. So it is mole power minus 3 and liter cubed and per second. So this is what you guys have got now. Mole power minus 3, liter cube and S power minus 1. Okay. So just check whether you have got this answer or not. Yes. So let me give you the unit of, yeah, okay, very good. So now let's do the unit of this reaction for solution as well as for gaseous solution. Okay, for aqueous solution and for gaseous solution. Suppose if I take for zero order reaction, the unit of rate constant for aqueous solution is mole per liter per second. So this is what we have discussed. Now, if it is a gaseous solution, then you cannot go for mole per liter now because mole per liter can be used only for aqueous system. For gaseous system, you have to replace this mole per liter with atmospheric per second. So in place of mole per liter, substitute ATM. Okay. Now for first order reaction, the unit is per second. In gaseous solution also it is per second because no concentration terms are involved. Then for second order reaction, it is mole power, mole, liter inverse and second inverse. So here it is ATM power minus 1 and second inverse. For third order reaction, mole power minus 2, liter power minus 1, minus 2 and second inverse. And here atm power minus 2. Okay, for any nth order reaction. So this is the formula we have to use to find out the unit. And in case of gaseous solution, instead of mole per liter, have atm. Okay, atmospheric pressure per second. Got it? In place of mole per liter, we are putting ATM, atmospheric pressure per gaseous system. That's all. The remaining things are same only. So students, is this clear? So all of you can able to understand, all of you can able to solve or find out the unit of rate constant for any nth order reaction, no? No doubt, right? Yes, very good. Okay, clear. Thank you, Sanika. Good. So now let's go with the characteristics of rate constant. Okay, all the points which we are going to discuss under this characteristics of rate constants are very important. So first of all, this rate constant K is a measure of the rate of the reaction. It is the measure of the rate. You can measure the speed of the reaction by seeing the rate constant. How to measure? How to know the rate of the reaction by seeing the rate constant? If the value of this K is very larger, then it means the reaction is occurring very fast. Okay? And smaller the value of K, it is a slow reaction. Larger the value of K, denotes a fast reaction. Smaller the value of K means it is a slow reaction. Got it? So just by looking into the values of K, we can able to predict whether the given reaction is a fast reaction or slow reaction. We can able to find out the speed of that reaction. Okay, very important point. So K is directly proportional to the rate. So different reactions, if you take, they will have different values of this rate constant. So all reactions may not have the same value of K. So every reaction will have different values of K. The value of this K changes with the change in temperature and with the change in catalyst. If we are changing the temperature for a particular reaction, then K value will also change. Okay. So for the same reaction, if I'm changing the temperature, then also the K value will change for that same reaction. And also it depends on the catalyst. If I'm using platinum metal as the catalyst, then that particular reaction will have certain K value. If I'm changing the catalyst from platinum to some other metal like copper, iron, then the value of K changes. Okay. So this is the next third point. Coming to the fourth point, the rate constant is independent on the concentration of reactant for zero order reaction. Why it is written like this? The rate expression for zero order reaction is equal to K into A power 0, where A is the concentration of the reactant. So anything to the power 0 becomes equal to 1. So rate is nothing but K. So here if you see, the rate constant or the rate for zero order reaction doesn't depend on the concentration of the reactant. The concentration term is not involved in the expression itself. Okay. So like the rate constant is also independent of the concentration of the reactant for zero order reaction. For first order, second order and all, rate constant is dependent on the concentration, because in the expression you will have the concentration term also. Clear? So did you all take down the points which I have taught you in this slide? Yes? Okay. So if you need some time to copy the points which I am teaching here, you can ask me. You can stop me and you can write, okay? You can take few seconds to write. Yeah, now let's go with one MCQ from this rate constant characteristics. What is the unit of rate constant for zero order reaction? Can anyone tell me? Sakshi, are you sure? Is it option B? Mahek is also going for option B. Okay, very good students. So option B is the correct answer. Rate constant is also called as Rate constant is also called as velocity constant, specific reaction rate, both A and B, none of these. What is this rate constant? Option A or option B? B. Everybody is going for B. Okay, let's check the answer. Neither A nor B is the correct answer. So the correct answer is option C. So in yesterday's class, I think in yesterday's class only, I have discussed about this rate constant in one of the slides. So in that I have mentioned that rate constant is also called as velocity constant because rate is called as speed and rate is also called as velocity, no? So it is also called as velocity constant and it is also called as specific reaction rate. So both A and B is the correct answer. Clear? Clear students? Yeah, coming to one more question. K is, just give me a second. Yeah. K is independent of concentration for a dash order reaction. Second order, first order, zero order, third order. The rate constant K is independent of. Very good. It is zero order. Just now we have seen, no, it is zero order. Unit of a third order gaseous reaction is. Unit of a third order gaseous reaction is. Is option D. Okay. Option D is the correct answer. So the next topic is integrated rate equation. So I think the rate constant part, its characteristics, its unit, everything is clear to all of you. So do you have any doubts from the rate constant and its characteristics? Does any of you have any doubts from the rate constant part? No doubt. Okay. So now, next we are moving on to a very important topic, okay, from this lesson, which is called as integrated rate equations. Integrated rate equations. So I'm going to derive an integrated rate equation for zero order reaction and for first order reaction. Okay. So let me start with the integrated rate equation first for zero order reaction. So here we will arrive at two formulas. One is for the integrated rate equation formula, the other is for rate constant. So those two formulas are very, very important. Okay. So here for zero order reaction, the rate is independent of the concentration of the reactant. So this is what we have discussed so far. And this is the information we already know. So now let me take a reaction in which a reactant is going to get converted into a product. Okay. Now for this reaction, I'm going to take that Cr as the concentration of the reactant. Let Cr be the concentration of the reactant. Then, if this is the case, then rate is directly proportional to the concentration of the reactant raised to their stoichiometric coefficient, which is called as N. And here for zero order reaction, that N is equal to 0 and K is the rate constant. Okay, for a zero order reaction, N will be equal to 0. So if I substitute N is equal to 0, then anything to the power 0 will become equal to 1. So rate is equal to K. Rate is equal to, what is rate? Rate is equal to K. So this is what we have been discussing so far. So we all know how to arrive at this relation for zero order, right? Now what I'm going to do, so since rate is nothing but the concentration with respect to time taken, so in place of rate, we had rate is equal to K. Okay, so in place of rate, I am going to substitute minus dCr by dt because reactant means the disappearance of the reactant. So minus symbol denotes the disappearance of the reactant with respect to time. Okay, so in place of this rate, we can substitute minus dCr by dt. Okay, so that will be equal to K. So take this dt to the other side. So what we will have, minus dCr is equal to K into dt. So now what we have to do, we have to integrate this equation. So on integrating this above equation, we have to integrate this. We have to integrate with respect to C naught and Ct, where C naught is the initial concentration and Ct is the concentration after some time t. Okay, these two are the limits. So it is minus dCr, and on the right hand side, you have to put the limits as 0 and t and kd. Okay. So now if we integrate this, where C naught is the initial concentration and Ct is the concentration remaining at time t, that is final concentration. Okay. Then now, if we substitute everything, what we will get. So you can, on integration, we can take the constant out. Okay, so since minus 1 is a constant, we are taking that constant minus 1 out. And here also k is a constant, so we are taking that k also out from this integration symbol. Okay, now we have the integration of dCr. So integration of dx is equal to x. So here x value is nothing but Cr. So what is integration of dCr? It is Cr. So already we have one minus outside this integration symbol. Substitute that. So integration of dCr is Cr. And we have to apply the limits. If we have some limits. So here we have C0 and Ct, no? So we have to apply the limit. So Ct is called as upper limit. C0 is called as lower limit. So substitute Ct and C0 like this in place of the Cr. Okay, with respect to Cr. So it will be equal to, so take the constant out, integration of dt. So here x is nothing but t. So it is t. So applying the limits, upper limit is t and lower limit is 0. Okay. So now what you have to do, you have to apply the upper limit first and then minus lower limit. So what we have minus concentration of our Ct and C0. So it will be equal to, keep this minus out, apply the upper limit, it will be Ct minus lower limit, C0. So we have to apply this limit in place of Cr. Okay. So we will get this, which is equal to, so for Kt what we have to do? Apply the upper and lower limit. So we will have k outside. And if you apply the upper limit in place of t, it will be t minus 0, which is nothing but kt. Which is nothing but kt. So you can take this minus symbol, okay, and you can multiply this. And if you do, so we will get a minus ct, minus into minus plus c0. So c0 minus ct is equal to kt. And if you bring this k to the other side, it will go to, t to the other side, it will go to the denominator. So k is equal to C0 minus Ct divided by t. And this is called as integrated rate law expression for zero order reaction. Okay. So these two equations are very, very important. Okay, this is the integrated rate law expression for zero order reaction. And here if you see this equation, okay, if you take this equation, so this will follow y is equal to mx plus c format. This follows y is equal to, so I am taking the same equation. So if Ct is taken out to the other side, we will have minus Kt and C0. So this equation is in the form of straight line where Ct is the y is equal to mx plus c, where m is the slope and slope is equal to minus k, and in x-axis I have to take t and in y-axis I have to take ct. Since the slope is negative, I will get a line like this, negative slope. So the slope of this line is minus k and the intercept c is c naught. So this point is the intercept and it is c naught. Okay. So straight line equation is y is equal to mx plus c. So this is what I have been explaining so far. Got it? So this is how we get a graph. And if you go for y, how far up and x is how far along. Okay. X is taken as t and y is taken as ct. And m is the slope of gradient. So that denotes how steep the line is. And c is the intercept. And that is the point where the line crosses the y-axis. Okay. So if we use all these concepts, we will get the graph which I have been drawn so far. Okay, we'll get a negative slope like this, and the C naught is the intercept point. So this is the graph which you have to keep in mind for zero order reaction for integrated rate equation. Okay, so the two reactions to that relation with this graph. These three things are very important for integrated rate equation for zero order reaction. So same thing we will discuss for first order reaction also. So that we will do in the tomorrow's class. Okay. So do you have any doubt from this mathematical derivation part of the zero order reaction integrated rate equation? So take the graph, take the two formulas. That is enough for solving the numericals. So the derivation part they may ask you in your school exams, but in NEET and the JEE exams they are not going to ask you to derive the equation. They will ask the problems from the final equation, okay, which you have to apply. So students, is this clear? Do you have any doubt? Okay then. Okay then. Thank you. Thank you so much for listening. See you all in the next class.